Corey, do you mind sitting? More that. There's a camera.
Oh, you need film? No, maybe.
Yeah. Okay, well, woo, Physics 24. Woo, yeah. Yeah, lab number 5. Woo! Lab number 5 is Faraday's law. Okay? Okay. So I just wanted to let everybody know that today we're being filmed. Okay, there's a camera in the back that you shouldn't sit in front of. And this is Chaya wanting to film this class because it's the best class. I just wanted to remind you that your homework is due today. And my PTC hours were yesterday from 6 to 8, in case you want to come next week. Next week, you also have your exam. Does everybody remember that? Well, I wanted to start by thanking you for your evaluations, although they have caused some trouble, as you can tell. I appreciate your comments very much. I will take into account both positive and negative comments, and just remember that my goal as your TA is for you to understand, and I'm here to help you at any time. So, who went to lecture? It's okay, you can, the camera only is looking at me. So some people didn't go to lecture, okay, some people have quit on that. So what do you think, what do we think about lecture? Honestly, this is a good chance to tell people how you feel.
I like being tired.
Okay. Teacher's pet. Okay, what do we think about the material? Is it confusing? Yeah. Yes. And I have a quote that relates to that. Okay? It's by Seneca. Does anybody know Seneca? Nobody. Okay, Seneca said, "It is not because things are difficult that we do not dare. It is because we do not dare that things are difficult." And today, I want to dare you to love physics. Love physics. And speaking of love, I would like to share with you a very sad story. A love story. That is also kind of like a mystery, so we're going to try to solve a mystery. But it's a love story. So this is the sad story of a lonely point charge. In a far Faraday land. That was a good one. I know. And this point charge had zero velocity. It was going nowhere, literally, with its legs. And all it ever wanted, really, was to move. Okay? So as its only friends, you smart people, have to help me give some velocity, apply some force on this electric charge. So what are some of the ways that we've already learned about how we could possibly make this move? So this velocity is zero. What kind of things can we do to this charge that would help it move? Nobody? How can I make an electric charge move? Yeah, we could apply an electric field at this point, and then it would experience a force that's Q times E, right? But in this sad story, there are no electric fields. Okay? There's only magnetic fields. And no matter how strong they were, these magnetic fields, the charge wouldn't move, right? Would it move? No, because its velocity is zero. If you just apply a strong B field, no matter in which direction, if there's a B field, no matter how strong, no matter how hard it tries, it won't win the heart of this electric charge. But then, how do you do it? How do you do it? Does anybody know? The suggestion/answer is you apply a changing magnetic field. No one seems excited. No one seems confused. Hey. So why would a changing magnetic field cause this? Well, the answer is that's what we observe. You know, that's Faraday's law. So let's try to understand Faraday's law because it really is something simple. And I don't want you to be confused about the simple things. Only about the complicated things like love. Okay, so let's consider charges that are not moving in a wire. Okay? So this wire has charges, and you know that if you put some battery and resistors, you could generate a current because of these charges that are moving around. But then what I want to do is I'm going to consider a B field, okay, that's pointing into the board. There's a B field into the board. And I'm going to ask what happens when there's a change in the B field. But to understand that, to understand Faraday's law, we first have to understand the concept of flux. Okay? Does anybody find flux confusing? Okay, flux is something very easy. Flux is just how much B field you have going through the ring times the area of the ring. Okay? And you're only interested in the perpendicular component. So if this is a side view of your ring, and the B field is going like this, you're only interested in the perpendicular component, which is B cosine theta. And this is why the flux is just how much B field is at this point, times the area times the cosine of theta. Okay? So that's the flux. And I'm claiming that a changing flux, okay, if the flux is not constant, so if you either change the strength of the B field or the area, a changing flux with time will cause the charges in this loop, in this wire, to want to move in one direction or the other. And what I'm going to explain to you now is in which direction they're going to want to move and how much they're going to want to move. Now, the how much they want to move is dictated by the EMF, right? The potential difference. So you could think of a change in flux through this loop as creating an effective battery, okay? Just momentarily, there's going to be something like a little battery here, and the voltage difference across it is the EMF that I'm going to explain now. But there is no battery, really. There's just a changing flux and a loop with wire. So the strength of this EMF, of the voltage difference, is very simple. It has a minus sign that has a meaning. It has an N and a change in flux with time. So let me explain first what this change in flux over time is. As I said, if either B, so this is the flux, how can I change the flux? I can change B, or I can change A, or I can change theta, right? And you've seen all of that in your homework. Who hasn't done the homework at all? Good. Okay, so if the strength of B is changing, or if the area is changing, or if the angle is changing, then you have a change with flux over time. And the bigger that change is, the more the charges want to move. The second part of this equation is this N. And this N is simply the number of turns of the coil. So this is a coil with one turn. Now I made it a coil with two turns. So more turns means that the charges are going to want to move more. And this minus sign is so important, it has its own name. It's called Lenz's law. Okay? And it's supposed to remind you of the direction in which the charges are going to want to move. Which way will the current want to flow? Okay? So let me explain to you now the direction, because that's also pretty simple, and people get confused with that kind of thing. So right now I have a B field that's pointing into the board. Okay? Let's say that this B field, the strength of this B field, is increasing with time into the board. Okay? So from this side view, initially it was this much, and then after a second or something, it was this much. So which way is the change of the B field? It's to the right. It was this much, and then it became this much, so the delta in phi is this much. So the change in flux is into the board. So I'm going to put my thumb with that, my right thumb. The change in flux is into the board, and then this minus sign reminds me that I want to oppose it. And then my fingers tell me which way the current will want to flow. Okay? Did everybody get that? The change in flux in this case is into the board. The minus sign reminds me to oppose that. And then my fingers tell me which way the current will want to go. Okay? Now remember to use your right hand. Okay, so this is pretty simple. Is anybody confused at this point? Is everybody with me? Yes?
How do you know that that's the right hand rule you want to use?
I'm telling you. Good question. But that's the point. You have to doubt everything I tell you. Yeah. Okay. So now, knowing this stuff, okay, now I've told you the direction, and I've told you how much this voltage in this circuit is going to be, the voltage difference. But now, you probably knew this already from lecture, right? So you probably all did the pre-lab, right? No. Because this pre-lab was hard. Because the TAs got this pre-lab wrong. Not me. But no, me too. Okay, so the first time. So what is this pre-lab asking you? Okay, you have a ring, and you have a magnet out here. Okay, this is the North Pole, this is the South Pole. And you're going to start bringing the magnet close to the ring. Okay, now there's a B field pointing away from the North Pole, like this, and into the South Pole, like this. Yeah? Okay, so as you're far, far away, there's no flux through the ring, because you're too far. But as you bring it closer, there's a flux, right? This B field, the flux, is it going to be to the right or to the left? Just someone say with confidence if it's to the right or to the left.
Right.
To the right. Right. Okay. That's the flux. Okay? And then when the magnet comes closer, because it's, it's coming closer like this, when it's at this point, there's going to be, it's going to be up here, really. So there's going to be more B field. So the flux, is it getting stronger or weaker?
Stronger.
Nice. Okay, so the flux, as the magnet gets closer, is going to get is going to be greater. Which way is the change in flux? To the right. The change in flux is to the right. I put my thumb with that. I oppose it because of this minus sign, and I see that the current should be flowing in this direction. There's current flowing in this direction as the magnet approaches the ring. And so if I were to have a resistor/light bulb right there, then that would light up. Okay? Because the current is flowing in this direction. Now when the magnet reaches the ring and it's inside the ring, the flux reaches a maximum. Right? So from then on, as the magnet goes through the ring and comes outside, is the flux going to be stronger or weaker? It's going to start to become weaker as the magnet is coming farther and farther away. Okay? i.e., if the flux was this much when it was right inside the ring, when the magnet gets there, the flux is less weak. It's more weak. It's less strong. Okay? So which way is the change in flux? The change in flux is now from here to there. It's that way. It's to the left. It doesn't matter which direction the flux is pointing. What matters is which direction the change in flux is pointing. And the change in flux is pointing to the left. So now I put my thumb to the left, but I remember that I want to oppose the change because of the minus sign. And now the current is flowing in the opposite direction, right? So what was happening? The current was flowing in one direction. Then it kind of stopped. Then it was flowing in the opposite direction. So the light bulb must have lighted once when I was approaching because of the current. Then it went off, and then it lit again when I reached over there. So in one swing from one side to the other, how many times did the light bulb light? Twice. Okay? So in a back and forth, that's 4 times. And in 3 back and forths, that's 12. Who got 12? Are you lying? Nice. Okay, so...
Can you explain again why it goes twice?
Yes, as you're approaching, we found that the current is flowing in this direction.
Right.
So there's a circuit that's being completed. There's current running through your resistor, and so the light bulb lights. Then right when you reach the maximum, the current is going to switch from flowing in this direction to switching to the opposite direction.
Does it go off?
Yes, it's going to go off for a second, and then it's going to light up again. Okay, so this lab today is all about exploring this equation in terms of coils, in terms of direction, and in terms of how does the EMF depend on the flux. Changing the strength of the B field and changing, well, I don't think you'll do any of that. But what are the different ways in which you can have a smaller or bigger change in flux? Okay? So is anybody confused? Really confused, lost? Was this helpful to anybody? Who found this helpful? Okay, good. So if you have any questions, I'll be here and coming around asking you, and try to do this and understand Faraday's law. Yes?
What's the rate of change of the flux?
What is the rate of change of the flux? So this is the flux. Okay? BA cosine theta is the flux. You could have a rate of change. If B is changing, if you know how fast B is changing, and A is constant and cosine theta is constant, then you know how much the flux is changing. Right? So if you're looking for delta phi, delta t, okay? If A is constant, then that's just a constant. If cosine theta is constant, that's a constant. But then if your field strength is changing with time, say someone gives you how fast the B field is changing with time, then this is given by this. Okay, thanks. Yes.
Is that considered a negative flux, or what is that?
So when it's coming this way, the fields are still pointing to the right. Which way is the flux? To the right still. Okay? But now, initially it was weak, but now as it's coming closer, it's getting closer. So which way is the change in flux? That way is the change in flux. You want to oppose that, so as you're coming from the left, the current will be flowing that way. And then again, there's going to be a switch.
This one, when you're starting the flux, instead of going down, you
yes,
just go back up?
Exactly. The flux is always pointing to the right. Okay, so let's do this pre-lab, and I'm going to come around and give you your previous week's labs.
Yeah, that's okay.